Okay, so yeah, so we continue chapter 2, and also hopefully we do some R implementation of some programs today. So we have the chapter 2 slides on the Canvas in Canvas, and also the chapter 2 lab slides in Canvas. So you can check those. Okay, so yeah. Do you have any questions about your homework? Oh no, the quizzes. Okay. So quiz solutions are generally available after 24 hours after the deadline. So the quizzes are due on Monday this week. So the solution will be available on Wednesday, 12 a.m. Okay, so chapter 2. Yeah, so last time we studied reducible and irreducible errors. Okay, so how to estimate F? So this chapter, the example is that we have sales as the response variable and 3 predictors, the advertisement amount on TV and radio and the newspaper. So one simple way to estimate Y is to fit this linear model. And we can fit a more complicated model. And that generally we have the 2 classes of models. One is parametric model and the other is non-parametric model. In parametric model, basically model is expressed as a finite number of parameters, and that number does not depend on the sample size. So suppose that we have 100 observations of y and x1, x2, x3. We have 4 parameters, but if we increase n is equal to 200, still the number of parameters is equal to 4. So it does not change and it does not depend on n. So in this case, we say the model is parametric. And the other model is the non-parametric methods. The model cannot be represented by the finite and fixed number of parameters. So for example, the y hat is defined by the mean y value of 5 nearest observations among x1, y1 to xn, yn. So often, when we want to see the y value, when x is given, that we choose just 5 closest observation to that observation, then we make average of those 5. I mean, average y value of those 5. That is one natural way. And in that model, okay, so we take 5 observations, but those 5 observations depends on our x value. Right? So new observation, x value of the new observation. So we cannot express in this simple way. So yeah, so in such a case that we say the model is non-parametric. So non-parametric models are usually more flexible and harder to interpret. Yeah, and perform sometimes better, sometimes worse. More data-oriented method, I can say. So, yeah, do you have any comments, questions? So mostly in 50-30 that we studied parametric models, linear models, logistic regression, and the many methods are parametric. We can say that maybe chi-square square test, that is just a test, but that isn't really based on parameter. So we can say it's a kind of non-parametric, but probably this example makes it clear, makes the difference between parametric and non-parametric methods clear. Okay, so yeah, so usually non-parametric models are more accurate. And the next one, sometimes we have the trade-off between accuracy and interpretability. So even parametric and non-parametric also has the same problem. Parametric models are easier to interpret. For example, what's the effect of x1? Do we have the positive relationship between x and y, or negative relationship between x and y? So that is very important in linear regression. So beta 1 is positive or negative. If beta 1 is positive, then the TV advertisement has positive effects on sales. But if we have negative effects on sales, the story is totally different. So the coefficient is important, and also the significance of coefficient is also important. But non-parametric models, okay, maybe this predicts sales better than parametric models, but we cannot really interpret what is the effect of the first variable. Sorry, maybe here that we have some confusion. X1, X2, X3 are three characteristics, three variables, and these are observations. So even though it looks the same notation, that we have different ones. Maybe I should say that this is maybe X11 or something like that. Yep. So X1 is the, okay, so this is the X1I maybe, and 2I, and X3I. And xi is equal to the x1i and x2i, x3i. I would say that. Yeah. And generally, the accuracy and the interpretability has trade-off. So more accurate model, sometimes harder to interpret. So for example, suppose x is a diameter of the shell, and y is the weight of the shell. Okay, so diameter is one-dimensional quantity. How about weight? What is the dimension of weight? So weight is the some measure for 3D objects. So the generally speaking, it's logical to assume that weight is maybe proportional to the cube of the diameter. So y is equal to alpha times x cube. So this is justifiable, and it's easier to interpret. But if we just use data and that we optimize this exponent, then possibly y is equal to alpha times x to the power 2.1 is better in terms of prediction accuracy. So which one would you choose? Oh, sorry, I got some chat. I don't know what's wrong with my, okay, yeah, that's fine. Yeah, so which model would you choose? You fit the two models, maybe y is equal to alpha times x cube plus error, and y is equal to alpha times x to the power 2.1. For if we just use data, this model is better. Okay, so this model is slightly less accurate. So which model will you choose if you are doing research? Maybe I should make a poll. So choice 1 is x cube, and the other is x to the power 2.1. Okay, so we maybe launch the. Yeah, so which one would you choose? So x to the power 2.1 is more accurate, but the x cube is justifiable, slightly worse performance. Oh, okay. So it's pretty one-sided result. Oh, but still, maybe two more people. Maybe one more. That is me. Okay, so actually, all people answered the cube, but in terms of the data science, maybe maybe you opt for the 2.1. So we don't have any unique correct answer. So either is fine. So some people use 2.1, some people use 3. Often scientists use 3, but the 2.1 is still the justifiable because it's best in statistically best.
Professor, I have a question.
Yeah.
Is this the same thing as the bias variance trade-off?
That's a good question. Actually, probably no, because the bias variance trade-off, we will study it later. That is the more complicated model has less bias, but the larger variance. But in this case, the two models have the same complexity. So in terms of the bias variance trade-off, no, I think it's not related. So just the yeah, so it's a different issue. So it just say that the second model has smaller variance plus squared bias. Okay. So it's a different issue. Yeah, that's a good question. So, okay. So we don't have a unique answer. That is the answer. Okay, so what's the accuracy? Yeah, sorry. I think it's really a good question that if this is the bias variance trade-off. For this specific example, no, but generally it may be related. Okay, so the accuracy and the interpretability. We have the many statistical methods. Some methods focus more on accuracy, and some methods focus more on the interpretability. For example, the subset selection. If we have 100 predictors, possible predictors, then we make the subset selection by AIC or cross-validation. Then we only use useful variables, then we can better interpret the model. And the lasso, I think the lasso is even more maybe towards the more interpretability and maybe less flexibility. So we lasso model assume that the only few predictors have positive coefficients. So others are 0. So that's more interpretable. So if we have 100 predictors, if we do subset selection by AIC, we may keep 10 variables as predictors, but the lasso maybe keep only 3 as the predictors. But still, we don't compromise the accuracy too much. And the least square, if we use all predictors, the less accurate, but the more accurate, but the less interpretable. And the generalized additive models. So this drops the linear relationship between y and x, but we don't consider the interaction between different predictors. Then it's more flexible, but we have less interpretability. And the three methods is, in short, we separate cases, then do some regression analysis. So it's more flexible and less interpretable. It also depends on how complex the regression model is, but yeah. And the bugging, boosting, this is also tree-based methods, but we have some repeated procedure of tree methods. So we apply tree method several times and take average or something like that. So it's less interpretable, but our estimated surface, I mean, if we fit y on x1, x2, x3, we have the surface, right, to predict y. And the surface is smoother and more flexible than tree models, but the less interpretability. And support vector machines, so this has the more advanced methods to identify nonlinear relationship between y and the predictors. So the less flexible, more flexible, but less interpretability. And yeah, the neural network, deep learning. So these are similar to support vector machines. Really almost no interpretability, but very flexible. And both models are flexible, support vector machine and neural network. But these days, neural network is more popular because the prediction performance is better generally. But the support vector machine is better for estimation. So neural network is very hard to estimate. If you study the theory and you apply the method, then you got error from the package because the solution does not converge or something like that. But the support vector machine has more solid background for the convergence and the more solid background statistically. Yeah, so these methods we will study in this textbook. Yeah, and now the we discuss the bias variance trade-off later, but now that we start the regression analysis and the classification analysis. So regression is for quantitative response, so typically real valued. Classification is for the qualitative response, such as binary, success failure, or multi-class, such as species ABC. And regression versus classification. So in some cases, the classification problem is regarded as a regression problem by considering probability. So if we have only two classes, male and female, so we can say that the one category is 1 and the other category is 0. So at least it's ordered. Then, sorry, the ordered. Anyway, so sorry, maybe it does not really matter here. Okay, so suppose we have only two categories, male and female, then we can consider the probability that some observation is male. So suppose that we want to predict the gender by the weight and height and the body fat percentage and the body water percentage and age as predictor. I think the women has generally the higher percentage of water, I think. And fat percentage, I think that it's larger variability for both genders, but on average, I think the women has higher the body fat percentage and height probably slightly smaller and weight also smaller, but also age matters for these variables. For example, for Americans, the weight is peaked at age 50 to 60 probably. And we have those findings. So if we have these variables, then we can predict the male or female with reasonably accurate model. Okay, so in this case, we can predict the probability of female given the predictor values. And that is often formulated by f of linear function of x1 to xp. Maybe x1 is weight and x2 is height, x3 is body fat percentage, x4 is body water, x5 age. Then we can make a linear combination of these predictors plus intercept, then f. Anyone remember what is function f for logistic regression? maybe some students who took the 50-30. Do you remember? Priyanka? Do you remember?
Yes, Professor.
Yeah. What's F for logistic regression? F of X is what? Hint, some fraction.
I don't remember, but
You
I
don't
think
remember?
I
Maybe.
think it's predictors.
Yeah, so the predictors that we have the beta naught to beta xp. So we have linear function, right? So if we have x1 to xp, then we have some plane. So this ranges from negative infinity to positive infinity, but basically we want to model the probability. So the left-hand side should be in 0, 1, right? So right-hand side within parentheses, it's negative infinity to positive infinity, but the left-hand side should range in 0, 1. So that's why we need this link function. Maybe any others? Antarang, maybe. You have taken 50-30, right? I have seen several ones. Do you see? Not sure. Okay, so maybe others, maybe Sai, you also took the 50-30, right? Or anyone else? Maybe just small bonus credits for your quiz. You can speak up. Anyone knows? So this is online class, so you can even see the book, right? Okay, so the logistic regression, we have the 1 plus the e to the power x and e of x. So e to the power x divided by 1 plus e to the power x, and we plug in this entire quantity beta naught plus dot 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 beta pxp as in this x. So if the number within f is larger, then this goes to 1. So if x gets larger and larger, f of x approaches to 1, and if x gets smaller and smaller, then e to the power x is almost 0. So f of x goes to 0. So you can see that this function f is like this. So 1 and 0, and it approaches to 1 if x goes to infinity, and it approaches to negative, 0 if it goes to negative infinity. So this is logistic regression. So in this way that we can use the regression model for this categorization problem if we have only 2 categories. Even if we have 3 categories, maybe we can evaluate the probability for the class A and versus class B and the class A versus class C or something. So if we evaluate the 2 different probabilities, then still that we can do similar thing. So the sum classification problem can be done with regression problem. So really, this kind of function is necessary for evaluate probability. So this kind of link function. So range is the domain is negative infinity to positive infinity, and the range is the 0, 1 or some finite interval. So a few days ago, I see some tweet from the mathematician, and the people say, the sine, cosine, tangent, arcs, the trigonometric functions are not useful after graduating schools, right? So many people don't use it. And he said, okay, so I'm a mathematician, but I don't use it so often. Then finally, he is doing machine learning these days, and he used the arctangent function. So tangent is the, this kind of function. So sorry. Range is negative infinity to positive infinity, and the domain is negative 2 pi to positive 2, sorry, negative pi over 2 to positive pi over 2. If we think about the inverse function of this, then arctangent, the domain is negative infinity to positive infinity, and range is negative 2 pi over 2 to positive 2 pi over 2. So if we just adjust the height and the scale, then we can make the range as 0, 1. So the many machine learning scientists use the arctangent function also. So he now says that okay, so we don't use the trigonometric function after graduation, and now at least we need arctangent function. So yeah, arctangent is also used, and sometimes there's some CDF, the probability density function, sorry, the cumulative distribution function of normal distribution is used as F. Yeah, so if you have taken my 50/30, then logistic regression is covered, and maybe some other instructors do not cover. And 5800, I think it does not cover the logistic regression. We will study this again in chapter 3 or 4 in detail. And this time we deal with the multi-category ones. So in 50/30, only the binary classification variable, but now that we have more extended ones. And yeah, and okay, so but at least the if response is continuous, I mean, sorry, the model for the continuous response and model for qualitative distance are the qualitative response. Those two models are totally different, basically, but the predictors may not matter. Even predictors are quantitative or qualitative. Basically, we can use the same model, and this explains the why. So okay, so this is a data set for predicting price of houses. And the data set includes price and the square footage and age and the style of the buildings. And we wanna, okay, so price is continuous variable, basically. So we can make, for example, a linear model to explain price by square footage and age. But also we can include style as predictor by setting up dummy variables, so-called dummy variables. So suppose that we have the 3 styles, ranch and colonial and the bungalow. And we have some baseline. So suppose that the ranch is a baseline. Then we set up an indicator variable for bungalow, and the other indicator variable for colonial. Okay. Then we have the indicator variable, 0, 1 variable, bungalow, and the colonial. Then we can just use these 2 predictors in addition to square footage and age. Then we can fit the model. So basically, coefficients for bungalow explains difference between ranch and the bungalow. Okay, so the model looks like the price is equal to beta naught plus beta 1 times square footage and beta 2 times age and beta 3 times bungalow and beta 4 times colonial plus some error. And this beta 3 explains the difference between ranch and the bungalow, because the ranch is the baseline, and if suppose beta 3 is 1,000. That means if the house is bungalow, the price is $1,000 higher than ranch. So this 1,000 is the difference between the price of ranch and the price of bungalow. Yeah. So often even the students finished 50-30. Sometimes the students don't really understand what this beta 3 means and what this beta 4 means. So this is difference between ranch and bungalow. So not just specific for bungalow. Yeah. And yeah, you can of course set up the variable for ranch, indicate a variable for ranch, but in this case, this variable is redundant, because if we think about this as x3 and this as x4 and this as x5, then intercept is equal to x3 plus x4 plus x5, right? So if we add up x3, x4, x5, then this is just the vector of ones, 1, 1, 1, 1, 1. So that is an intercept. So we cannot estimate estimate the coefficients of these 3 variables plus the intercept. So one variable is redundant. So to make a linear model, basically all predictors should be independent, linearly independent. So we should omit one of these. So we should not use this one. And which one should be the baseline? It really depends on the problem, but if you don't have any idea, maybe you can make the largest group as the baseline. Yeah, often the students do analysis of some demographic data and the races, like the white and African American, Asian, and the Hispanic. I suppose the Hispanic is not the race in some sense, but the Hispanic and the others. And if others is the base, it's really hard to interpret the result. Suppose we got the coefficient of the white is, okay, so suppose 0.3 for some model, and how to interpret 0.3, that is difference between white and others, and what the others, it's not really clear, right? If the largest group is the baseline, usually interpretability is higher. Yeah, so also it's important to mention that since this represents the difference between bungalow and ranch, so it only says that we have, if beta 3 is significantly different from 0, that means the ranch and the bungalow are significantly different, but we don't really know other cases. We don't know the difference between bungalow and the colonial, for example. Yeah, so but anyway, so by using these dummy variables, we can transform the categorical variables into continuous predictor. Actually, these are indicator functions. But yeah. Do you have any questions so far? Okay, so yeah, so now that we are thinking about the assessing model accuracy, so what's the way to measure the quality of fit, and what's the bias variance trade-off, and what happens if the problem is classification? So basically the first two items are for regression problem, and this is for classification problems. And the most popular measure of fit is training MSE. Yeah, so mean square error. So mean square error is defined as this. So yi is actual, the y value, and yi hat is our fitted y value. So difference is considered as an error. So we take the summation of squared errors, then divide by the sample size. So this is a kind of the averaged the squared error, so mean square error. Yeah. So if we use the f hat and the xi to express this MSE, that is 1 over n times summation I is equal to 1 to n yi minus f hat of xi square. Yeah, but the problem of this measure is that this measure only evaluates the error for our sample. Usually, our sample is the training set, and after developing a regression model, we want to apply that model for new data, and the key is the error size for new data. So not the existing training data. So that is a little different. So that is a problem, but at least it's easy to calculate. It's easy to calculate training MSE. Yeah. And the problem on training MSE, and the training MSE gets smaller as model is more complex. But it does not mean that the expected error size for new observations gets smaller. For example, suppose that we have 100 data points, and we have, okay, so polynomial of degree 99. So we consider the model that the y is equal to beta naught plus beta 1x plus beta 2x square plus up to beta 99 x to the power 99 plus epsilon. So how many parameters? We have 100 parameters from beta naught to beta 99. And if we fit the model, so just plug in x1, y1 to x100, y100. Then we have 100 parameters for 100 equations. So we can perfectly solve this equation if we don't have any dependence. If we have the same x values for some observations, then that's a problem. But if everything is different, basically this model is always perfect in the sense that the residual is 0. So training error becomes, converges to 0 as model becomes more complex. But that does not mean that this model has 0 error for new observations. So you can think about it, just we have 100 observations. 100 maybe too much, so I just write the 10 observations here. 1, 2, 3, 4, 5. Okay, so 10. Then if we use the 9-degree polynomial, then of course we can fit the perfect line like this. But it does not mean the new observation is predicted correctly. So we have still some error. So in this sense, training MSE is problematic. It underestimates the error size. Yeah, so this is, you can see this, the left one, to see that situation. So we have how many observations here? Maybe 50, about 50 observations, and we fit several curves. This yellow one is the degree 1. So that means that we have 2 parameters. We say p is equal to 2, slope and intercept. And it's reasonably good, but maybe if we use the cubic curve, that is this black one, probably it represents tendency better. So this is cubic curve, so p is equal to 4. And if we use more complex one, sorry, red, sorry, I'm sorry, the blue one. Sorry, then maybe I have to explain the again. So suppose that these observations are generated by this black line. So black is the true line, but we don't know true but unknown curve. This is simulation, so we know the black curve, but usually we don't know the truth. Black is true but unknown. And the yellow curve is the a straight line, so it has 2 degrees of freedom, slope and intercept. And the blue line is cubic curve. So this is p is equal to 4. So we have 4 parameters: the beta naught plus beta 1x plus beta 2x squared plus beta 3x cubed. And the green one, it's much more flexible. That we have maybe 20 or 21, 20 p's around 20. So we have the 19-degree polynomial, maybe 20. You can see 20, maybe 23 or something. So p is 23. So we have the degree 22 polynomial. So it's much more complicated, and it fits this data well, but it sounds that it's too noisy. So it's too volatile. Maybe the true relationship is closer to blue one. And actually, this is a simulation, and you can see that actually the blue line is closer to the truth, the black line, and the green line is the too volatile. So yeah, just ignore the red one, and we can only use this one. And the training error is represented by this gray line. Training MSE. So training MSE gets smaller and smaller as p gets larger. So yellow line, the largest. So basically the discrepancy between these points and this trend line is largest on average. And it gets smaller and smaller. So green line has the smallest training MSE, but we don't expect that this is better than the blue one. So the training MSE is a problem to compare models with different flexibility. Then we introduce test MSE. So we basically divide the data set into D1 and D2. And we fit the model with D1. So we estimate these curves by D1 only. Then after that, we use D2 to evaluate the error size. So this is more practical. Practically, we have training set, then set up the model. We estimate the model. Then we have new data set and to evaluate, to apply that model. So the error size for new observations are important. So this test MSE is more practical. So we divide the data set into D1 and D2, and we fit the data with D1 and evaluate with D2. So this is called the test MSE. So test MSE is more accurate measure of expected error. So actually the previous one, this line, the red line, so this is the test MSE, while this is training MSE. So the training MSE, so suppose this is just the data D1, and we have another data set to D2, and we evaluate the MSE with the estimated model with the new data set, then test MSE is smallest for blue one. That is pretty reasonable because the green one is unnecessarily the volatile, fluctuate too much. So test MSE is considered a better measure for prediction accuracy. Do you have any questions? So we will study the cross-validation in later chapter 4 or 5, 6. And that basically discusses the some side effect of using the test MSE. So at least if data is limited, we have to divide the data set into training and the test set, and that is not good because the training set gets smaller. So that can be solved by using cross-validation, but still that we have some drawback if we use test MSE. We can only use a partial data for training.
I do have a question,
Sure.
Professor.
Yeah.
Maybe it's not something that we're going to talk about right now. Maybe it's something you'll cover later, but when you split your data into tested and training, is there any procedure for that? Like if you talk about like, I don't know, I feel like, should you be concerned that your, I don't know, the distribution of your training data versus your test data or anything like that?
Yeah, so it really depends on the data type. So if we have just the random sample, such as, randomly selected, 1,000 patients or something, then just divide the data randomly. But sometimes that's not appropriate. So suppose that we have time series data, and the time series data from maybe 1900 to 2020. Then usually we use the first 90 years of data as training and the last 30 years as test. Because if we just ignore the time structure, we have less, flexibility to model the using, the time point. So in such a case, we have to take the training period and test period, not take the observations randomly, but maybe first 100 years, first 90 years, and the last 30 years or something like that. So it really depends on the data set. Yeah.
Okay, so it's largely just random. You just say, give me 20% and 80% or some split, and you take what you get.
Yeah, so if the random sample, then the make randomly. Yeah, the make make selection randomly. Yep.
Okay.
Yeah.
Cool. I'm just curious.
Yeah.
Thank you.
Yeah, I think that's a really good question. So it really depends on the situation. So some observations are dependent, for example. So suppose that we have the 20 patients and the 20 patients have 2 lungs, and so the sample size is 40. So in such a case, we should take the random sample. So we randomly take patients, maybe, the 7 patients as the training set and the 3 patients as test set or something like that. Maybe, sorry, the 20. So maybe 15 patients as training and 5 patients as test or something. So not the lungs. Yeah, that is usual way to go. Yep. And and also the split, the percentage, it's not clear. There may be 2/3 as training and 1/3 as test. That may be a ballpark estimate, but it really depends on the case. Yep. Other questions? Yeah. So to split randomly, that is the basics, but in some cases we cannot do that. That is the point. So next, the bias variance trade-off, the one of you mentioned before. So when we make a model, that we have the trade-off between bias and variance, and this example explains the why we have trade-off between these two. And actually, we haven't defined bias and variance, but we will define it mathematically in the following slides. So suppose that we want to predict the height of a male by his foot size. That is a reasonable model. And we have training data. Possibly we have larger data, but okay, so maybe most relevant observations are these 5. So the first male that has the foot size of 27.2 centimeter, and his height is 176. And we have 4 other observations. We have, in total, we have 5 observations. Then we have another observation, new observation, and his foot size is 28.0, but height is unknown, and we would like to know his height. And 2 methods. The one method is, okay, so we pick up this observation because his foot size is 28. That is closest, actually almost the same as this new observation. So we expect that his height, the new observation, so the male's height is the 176 centimeter. Y hat is 176. And the other way to estimate it is, okay, we have 5 observations. So observations have some variability in height. So if we average out, then it stabilizes. So it's good to take average of these 5 heights. So our estimate is 178.8, which is a better estimate. We cannot really say. Maybe the first one is more accurate in the sense that we match this, foot size. So, probably this is the best estimate we can say. But the second one is more accurate in the sense that we average out 5 people. So the estimation is more reliable. And the first one that we say we have a smaller bias. Right? So suppose that maybe more extreme case, maybe we don't have these ones. Okay, so these ones. Then if we see these 3 people, if we use this as an estimate, it has probably a smaller bias. If we use this and this, then these 2 people are probably higher than the new observation. So maybe we have some bias if we. Sorry. This maybe we have to explain in another way. So yeah. So if we only use this person, we can avoid bias. If we use these 2 person, maybe so these 2 person have the larger foot size, so they may be higher. So we may get some bias. So we should use only this one. So it has y hat has smaller bias for this case. But the second case, we have smaller variance. This is maybe easier to understand. If we average out 5 observations, usually if we average or take average of 5 observations, then the variance of x bar is equal to maybe 5/1 times the variance of x just 1 observation. So the variance gets smaller by 5 times smaller, so it has the smaller variance. So B is better in terms of a smaller variance. And then we can mathematically show that this bias and the variance have trade-off. So suppose that our model is y is equal to f of x plus epsilon, and f hat is estimated by some model. Yeah. So f hat may be the picking up the closest person, and another f hat is the taking average of the 5 closest observations. So we have 2 different estimates. Okay. And then we have the trade-off between bias and the variance. So what's the error size? Error size, expected error size is this, the y naught minus f hat, f naught hat, f hat naught. So here the f naught is f of x naught, and the f hat 0 is the f hat of x0. Then f hat of x0 is our estimate, but we can decompose this into, at first, in this way, because the y naught is equal to the f0 plus epsilon. Then further, we add this expectation of f0 hat and the negative expectation of f0 hat. Then we can now decompose this into 3 terms. So basically this portion and this portion and this portion. And at first, note that this is based on the new observation, so observation 0. And this f hat is based on old observations, x1 to xn, right? So this is for x naught, y naught, right? So these are different observations, and our assumptions are observations are independent. So these are independent. So yeah, these are independent. And also note that the expectation of epsilon is 0. So if we think about the expectation of the product, expectation of the product, this one times this one, then expectation decompose because they're independent. if independent, if x and y are independent, then expectation of xy is equal to expectation of x times expectation of y. And if expectation of epsilon is 0, so that means the cross term it becomes 0. And the first one, f naught minus expectation of f0 hat. This is constant. You can see f naught is just a true model, so this is constant. And f hat is random, but the expectation, after taking expectation, it's constant. So this is constant, and the expectation of epsilon is 0. So the cross term is also 0. Right? So almost everything is 0. And here also we have the product of this and this, but you can see that the second term expectation is 0. Expectation of f0 hat is expectation of f0 hat. And the second one, expectation is expectation of f0 hat. So after taking expectation, second term is 0. And with the same reason as the first and the third term, interaction is 0. So actually the cross terms, interactions are all 0. So just this term and this term and this term. And the first one is called bias of f hat, because this is difference between the expected f hat and the true f. So we can say bias. So the entire term is bias square. And the second term is by definition, the variance of f hat. And the third one is expectation of epsilon square. And this is so-called the irreducible error. So this part is reducible error. And reducible error is decomposed into the square of bias and the variance. So now that you can see that if the estimator has larger bias, then the variance becomes smaller. And if the bias is larger than the the bias is smaller than the variance should be larger. So we have the trade-off between the bias and the variance. To be accurate, square of bias and variance. Yeah, so the implication. So to minimize expected squared error, the model has to balance between bias and variance. And if the expected squared error has the same size, there is a trade-off between the bias and the variance. Of course, we have the inaccurate model, but if expected squared error is the same, then we have trade-off between bias and variance. So we can say that test MSE have the same size for two models. Then one model may have a smaller bias, but in such a case, the larger variance. So this is the numerical example of the trade-off between bias and variance. So black one is true line, and the yellow, blue, and green are estimated model. And so the yellow, blue, green, which has the smallest variance? Anyone? How about any person? Especially if you don't turn on the video, then I appreciate if you answer some questions. Shuraya, what do you think? Which has the smallest variance? Smaller variance means more stable model.
Maybe the green one is closest to the black line. So maybe the green one.
Green one is the closest to the circles, but it's not stable, right? So if we have different data set, the green graph will change. But the yellow one, that doesn't change much. You can see that if another data set is from the same truth, but like this. yellow one doesn't change much, but the green one changes because, for example, this one affects green one positively, but this one affects green one negatively. So probably the new green graph becomes
Okay, yeah, I see it.
like this, right?
Then maybe it's the blue one.
And the blue one, maybe it's a little bit hard to distinguish yellow and the blue one. That's true. But the blue one, if you think about the equation y equal, so yellow one is this, right? And the blue one is we have cubic curve, so this one, right? So if you have fit several linear regressions, then if we have more parameters, it's more unstable. If you compare the first one, the yellow one, and the blue one, you know that the yellow one is more stable because we only have 2 parameters. If we estimated 4 parameters, often these have the larger variance and the not significant, right? So actually the yellow one has the smallest variance in this case. So I would say that the yellow one, the small variance, but the green one, larger variance. This is in the middle. So how about bias? Which one has smallest bias?
The green one.
Green one, yes. Yeah, smaller variance. So the other way around, right? So the it really depends on the accuracy also, but if the same accuracy, then this. You can see, for example, around here, you can see around here, maybe around 65. Obviously this yellow one has larger bias. So the truth should be this black one, so around here, but the yellow one is much below because the model is too simple, so large bias. Green one, it's volatile, but the bias is small, right? Sometimes, blue one looks smaller, but actually on average, if we take the expectation, the green one has the smallest variance. So this is another explanation of the trade-off between squared bias and the variance. Yeah, so maybe accuracies may be different. So maybe, possibly, maybe I would say bias square. Possibly in total, the blue one has the smaller, the error size, expected error size. That's possible. So if accuracy is the same, the sum of bias square and variance are the same. But possibly, yellow one has very large bias and the green one smaller bias and the blue one moderate. And this is the other way. That's possible. So that the blue one is most accurate. That's also possible. But at least if we compare just squared bias and the variance, certainly yellow one has largest bias, squared bias, and the smallest variance. Yeah. Any questions? Sorry, I got a question. What's epsilon? Epsilon is the error size. So always the statistical model have error size. So intrinsic error, that is epsilon here. Yeah. So sometimes I don't see the chat message. So yeah, you can ask you can speak up and ask questions. Yeah. Okay, so this is the regression analysis, and the next topic is what happens if it's classification problem. So for classification problem, Okay, so the maybe we start with an example. Classification problem looks like this. So this is an example to make a guess on whether the person is the child or adult female or adult male. So suppose that the admission fee is different among these three groups: the child and the adult female and adult male, maybe all you can eat buffet or something. But we don't have a good system. So just based on height, we judge whether the person is child or adult male or adult female. Then, okay, so this is criterion. Then, suppose we set some rule. Suppose X is less than 145 centimeter, then we regard that as child. And between 145 and 165 adult female, more than 165 adult male. Okay, so suppose in this case, then if the probabilities are given by these numbers, so these are correct decisions, and the others are incorrect decisions. So just that the one simplest way to evaluate error is how accurate it is. So how large these probabilities are. So the definition, a measure of error for classification problem. The error rate is a natural measure of training error for classification problem, and this is defined as this. So suppose that the observations are x1, y1 to xn, yn, and the yi is in a group G. So we have a group of 1 to G. So that we have G classes. Then the error rate is this. So yi and yi hat are different for some observation, and we take the average, the sample average over the all observation. So yeah, so we make an estimation, and suppose we have the observation x1 to xn, maybe x10, and we have the y1 to y10. Y1 to y10 is like 1, 1, 2, 2, 3, 4, 4 G. Then this is y, and we have the yi hat. We have estimate. So estimate is maybe 1, 1, 2, 1, maybe 3, and 4, 5, ... something. Then we make an error here, and we make an error here. So we count the number of errors. Then this is an error rate. Yeah, and yeah, so this is a kind of the training. It corresponds to training MSE. And if we want to think about the test error, which corresponds to test MSE, then we have to take expectation of the y0 is not equal to y0 hat. So what's the probability that this happens? And this can be calculated by sorry, this is which is also defined as the sorry. So to estimate the test error, basically we have to estimate this one. So we define the same one for the test data set. So this is for training data set, but if we calculate this for test set, that is the test error rate, and it can be used in the same way as test MSE. So if we want to get a more accurate prediction model, then we should use test error rate. Yeah. And how to make a decision. how to make this decision, and that is explained by this one, the Bayes classifier. So this is the probably the simplest classifier based on the probability. So suppose that we can calculate the probability of y is equal to j when x is given. So height is given, then we see what's the probability of that person is child or adult female or male. If probabilities are given, we make the decision based on the largest probability. So if the x is given, then the probability of child is largest, then we regard that person as a child. So that is called the Bayes classifier. So this is explained by this table. So if x is less than 145, suppose that the person is 70% child, then this 70% is larger than this 0.2 or 0.1. So we decide that this person as a child. So that is the Bayes classifier. And the Bayesian error rate is calculated by 1 minus the other cases. So Bayes error rate is equal to 0.3 for first observation. So maybe, sorry, Bayes error rate is 0.3 for this one. And if for the second group, x is between 145 and 165, if that person is 60% adult female, then we decide that person as the adult female, but we make 40% error. So Bayes error is 40%, and the last one in the same way, 40% the Bayes error rate. So Bayesian error rate is calculated in this way. So Bayesian error rate is given only when x is given. Yeah, so this is the most basic way to decide the which category each observation belongs to. We have a similar quiz to this one for today. Yeah, so special case, the binary case. So binary case, we decide the y hat is equal to 1. Maybe I would say y hat is equal to 1 if this probability is larger than 0.5. And y hat is equal to 0 if estimated probability of 1 is less than or equal to 0.5. Maybe you may want to include equal sign here. So it maybe just depends on your preference. Yeah, but the 0.5 is the threshold to divide the y hat value. Y hat is either 1 or 0. But of course, in some cases, you want to get the different threshold, because basically this is based on the risk of the decision. So suppose that the truth is, y is equal to 1 and y is equal to 0, and our estimate is 1 and 0. Then this is correct, so it's fine. But the different errors have the different risk. So think about the diagnosing cancer patient. So if the truth is malignant, suppose 1 is malignant, but we diagnose as benign and we don't do any treatment, then the patient may die. So that has a larger risk maybe. And but the other way around, if the patient is benign, but we give some drug, then suppose we don't have side effect, still it costs some, maybe $100 per month. So it has a smaller risk, but still we have a risk. So if R1 and R2 have the same amount, then the 0.5 is a reasonable threshold. But in some decision-making problems, maybe the threshold different than 0.5 may be appropriate in some cases. Yeah, so this is the classification. Yeah. Yeah, so we don't have really concrete example here, but suppose we have some categorization problem with the two predictors x1 and x2. So basically, y value is 1 if the circle is maybe purple, and the y value is 0 if the circle is orange. Then we have some decision boundary. Then so this line represents the line that probability of y is equal to 1 is equal to 0.5. Maybe probability of y given x value is equal to 0.5. So this is the boundary. So in this case, this region is regarded as y hat is equal to 0. And the other area, so this area is regarded as y hat is equal to 1. Yeah, so the next time that we discuss the concrete procedure on how to make this decision by a simple method called the k-nearest neighborhoods. Okay, so we stop here, and so today we have a couple of quizzes, and I think that I assigned 4 quizzes, but the last one we couldn't cover today, so you can do the first 3 quizzes, I think. Yeah, okay, so that's it for today, and quizzes are already available and due on Thursday night, and yeah, see you this Thursday.
Fair.
Thank you.
Bye,
Thank you.
everyone.
I mean, that's everyone with everything.